We will now talk about limits, and we'll be talking about limits of functions of two variables. So let's say we have a function f of xy, and we are looking at the limit of f as xy approaches the point AB. So here AB is a fixed point and xy is approaching AB. So if we write that this limit is L, then what do we mean? What do we mean by this symbol? Well, the limit of f as x approaches AB is the limit of f as xy approaches AB is L. It means that f of xy can be made to be within any open interval centered at L by choosing any xy in a suitably small disk centered at AB. Once again, the limit of f as xy approaches AB is L if f of xy can be made to be within any open interval centered at L by choosing any xy in a suitably small disk centered at AB. Okay, so what we are saying is that if we can make the value of f of x to be within any small epsilon of L by choosing xy in a small disk centered at AB. So given any small positive number epsilon and a open interval of radius epsilon centered at L, if we can find a small disk centered at AB, so that for any xy in this disk, f of xy is in this open interval. So once again, if for any small positive number epsilon and an open interval of radius epsilon centered at L. Okay, let me rephrase that again. So if for any open interval of radius epsilon centered at L, we can find a small disk centered at AB such that for any xy in this disk, f of xy lies in this interval. Then we can say that the limit of f is L as xy approaches AB. Now let's recall that the limit of f of x as x approaches a is L if and only if the limit of f as x approaches a from the right is L and the limit of f as x approaches a from the left is L. So if I in the case of a function of one variable, and when we are taking the limit at a, notice that we can approach a only along one line and from two directions. Now, if we have a function of two variables and we have a point AB, then there are too many ways to approach the point AB. That is, we can approach the point AB along many different lines, infinitely many different lines. We can also approach AB along curves, which are not straight lines. So you can see that there are many ways you can approach a point in the plane. And in the case of a function of one variable, you can approach a only along this line and from just these two directions. So the limit of a function of two variables is a bit more complicated than the limit of a function of one variable. So let's look at some examples. So let's say I am looking at the limit of x squared minus y squared divided by x squared plus y squared as xy approaches 0, 0. Now notice that if we approach 0, 0 along the x-axis, so so here is, let's say, the here is the x-axis, let's say, and we are approaching the origin 0, 0 along the x-axis, so basically along the points. So then we have the points x comma 0. The point x comma 0 is approaching the origin. So in that case, the function, the value of the function on the x-axis would be, well, y is 0, so it would be x squared divided by x squared. So notice that because we are approaching 0, 0 along the x-axis, the value of the function on the x-axis would be what? Well, on the x-axis, y is 0, so the value of the function is x squared divided by x squared, which is 1. So that means as we approach 0, 0 along the x-axis, then the limit of the function is 1. Now notice that if we approach the point 0, 0 along the y-axis, well, this time on the y-axis the x coordinate is 0, so if we delete x squared here, then we get negative y squared over y squared, so that's negative 1. So if we approach 0, 0 from along the y-axis, then the limit is negative 1. So we see that the limit is 1 when xy approaches 0, 0 along the x-axis, and the limit is negative 1 when xy approaches 0, 0 along the y-axis. So because of that, since these two limits are different, we can say that this limit does not exist. Let's look at another example. So here we have the limit of xy divided by x squared plus y squared, here xy is approaching 0, 0. Now, so once again, if we take the limit along the x-axis, then along the x-axis y is 0. So because y is 0, we see that this function has value 0. So on the x-axis, the value of the function is always 0. So the limit would be 0. And if we approach 0, 0 along the y-axis, then the x coordinate will always be 0. So then the value of the function on the y-axis is 0. As a result, the limit will also be 0. So we see that if we approach the origin from along the x-axis or the y-axis, we are getting the same limit 0. Is that enough to say that the limit we are looking at is 0? Well, the answer is no, because what happens when we approach the origin along the line y is equal to x? Well, along the line y is equal to x, if we approach, so here is my xy coordinates, and so now we are approaching, let's say we are approaching along the line y is equal to x. So on this line, the points are of the form xx, right? Because the x and y coordinates are the same. So in this case, the value of the function would be what? Well, x and y are the same. So replace y by x here, so you get x squared. Replace y by x here, you get x squared. So you get x squared, and here you get 2x squared. So that ratio is half. So along the y-axis, then the limit is half. So if xy approaches the origin along this line, then the limit is halves, which is different from 0 that we got when we approached the origin along the x or y axis. So we see that once again that the limit as xy goes to 0, 0 of x squared minus y squared over x squared plus y squared does not exist. Okay, so I'm going to stop the video here, but I have more to say about the about limits and continuity.